Bluetooth. Get it straight.
Okay, let's take a look at the sonar transducer problem that we were dragging from a boat in the class. This is a similitude or modeling problem where we're going to use wind tunnel or other results as our model to scale up to the real case, which is the prototype. So we've got the prototype, which is the boat dragging the sonar through the ocean, and we've got the model, which is a similar object that's put in a wind tunnel to determine how much drag will happen on that. So a couple of things that are different here. One, the sonar object is actually 1 foot in diameter. The model system is only 6 inches. And obviously the wind tunnel is working with air, and the sonar is being dragged through water, and it's pretty cold water, so we'll have to track the viscosity on that. So the key here is if we assume that the problem or the model is similar to the prototype system, then the dimensionless groups are the same. So we have this drag coefficient, which is actually the force of drag divided by this energy term rho v squared d, so that's the velocity squared times the diameter, and that's going to be a function of the Reynolds number. So there's basically 2 pi groups here, the one related to the drag coefficient and one related to the Reynolds number. So for similarity, the model Reynolds number has to be the same as the prototype Reynolds number, and the model drag coefficient has to be the same as the prototype drag coefficient. So we know enough from the given information about the prototype to calculate a Reynolds number, because we just need the velocity, the diameter, which we have, and density and viscosity terms. Remembering that we can also use this new term, new NU, not NEW term, to be the kinematic viscosity, which is just mu, regular viscosity over here, divided by the regular viscosity divided by the density. So if we look that up for seawater someplace at 5 degrees C, we would get this number. So that's a lookup number. The velocity is 5 nautical miles per hour. That's what a knot is. So that's kind of strange. So we had to convert that to 8.44 feet per second. And if we did all that, we would get a Reynolds number of about 500,000. So we are given, remember back up here, that the force of drag on the model in the wind tunnel is 5.58. And so that would tell us what speed the wind tunnel is run at. And knowing that we have the same Reynolds number for the wind tunnel, that's what we just assumed when we said that we have a similar system. So that's how this modeling works, and that's really the key to these problems, is you calculate the Reynolds number for one side, but then what for the other side. So we can say that the Reynolds number is known. We can calculate what the wind tunnel velocity would be. Remember, now we're going to put in the viscosity for air, which is another lookup number, and diameter, which we're given, has 0.5 feet now. We're in the model system. So if we do that, we see that the model is running much faster with air, and you need more speed in order to generate the kind of drag that you would expect when you're dragging this thing through water. So then you can go back to your drag coefficient expressions here. And those also have to be equal. And we know everything except the force we expect on the prototype in the ocean. So we're given this one, remember. That comes from the wind tunnel. And all these guys are lookup terms. These guys are ones we calculated or given, and the diameters were given. We just put those all together, and we see that this is the kind of force we should expect on the prototype sonar system in the ocean. Okay, this is the Buckingham Pi example that we did in class on Thursday of week 11. And so this is from chapter 7, and it's pretty easy, but a little bit long. So take a look at it in detail this time and then try some practice problems. So in this one, we are interested in understanding the pressure drop as you flow through a pipe. And we've got a pipe of length L, and the velocity, the average velocity is V. And so there's the V, there's the L. The other important parameters that are given here are D, the diameter of the pipe, viscosity, the density, of course, of the fluid, and this kind of new thing called the roughness that we'll hear a lot about in chapter 8 when we talk about pipe flow. So this has to do with the roughness of the pipe, roughness, height, how rough is the little edges of the pipe compared to the diameter of the pipe. So because our parameter of interest is delta P, make that our dependent variable, and then we have 6 other variables here. So in total we have 7, and the dimensions of these are as so. There's 3 main dimensions here, mass, length, and time. So the number of pi terms will be the number of variables, parameters, minus 3, the number of dimensions, which is 4. There should be 4 pi terms here. So we need to choose 3 repeating variables. And remember, we try to choose simplest ones without making them too similar. So the simplest one would be maybe diameter, because that just has units of length. The next simplest one would be velocity, length per time. And then you have to pick another one that would not be L because it's too similar to diameter. So we'll pick density, has a little bit simpler units than viscosity. So then we go through this 4 times because there's 4 pi terms. So we basically take one of the non-repeating variables. In the first case, we choose our delta P usually, and we take that times the repeating one. So here's the repeating one. So these are the ones that are going to be seen again and again. So there's the rho, the V, and the D, and we raise them to the A, the B, and the C. We put their dimensions in like so. Remember, these ones have the A, the B, and the C, and the non-repeating variable, in this case delta P, has no letter up here because we just leave that the way it is. The objective here is to pick A, B, and C so that we cancel out the units of delta P. So we can take it one at a time. For mass, we want to get a 0 here. So we let 0 on the left-hand side equal A plus 1. So there's 1 mass here, so that's A here, and 1 here. So that means that A is equal to -1. That one's easy. So for length term, we have length cubed on the first term. We have length to the B, it's length to the -3A on the first term. It's length cubed and it's in the denominator, and we have an A up here. So this gives us a -3A. And for B, we have a length in the numerator and it's raised to the B, so we have a B here. In the third term, we have length to the C, so we have a C there. And in the fourth term, we have length in the denominator again here. And so that gives us a -1. So those 4 terms, can't quite figure it out until we do time. And time is, we have the time here raised to the -B. We have -B. In the fourth term, we have time to the -2. So minus B minus 2 equals 0. So B equals a -2. In order to make this -2 cancel out, we have a -2. And so lost my pen there for a second. -2 minus 2 is 0. So we have, we work out the C, we'll find out that C equals 0. We change the A, B, and C into these numbers we've just solved for, and that gives us our first pi term. And if you check the units on this, they should all cancel out so that you have a dimensionless group. So for the second one, we bring in our next non-repeating variable, so that could be any of them that weren't chosen. So that's a mu, and we have our typical 3 repeating variables, the ones that we are always going to use in this problem. So again, we go with A, B, and C, and no letter here. We're trying to make all these equal 0, cancel out, in other words. And so again, we get A, -1, C, -1, and B, -1. All three are -1, and we end up with this pi term right here, which is actually equal to 1 over Reynolds number. So that's where we quit in class. But we could actually go through the other two, pick the same 3 as usual. And now we're taking L as the non-repeating number, A, B, and C for the repeating variables, nothing for the non-repeating variable. In this case, we find that A equals 0 and B equals 0. The only thing we have is C, which is a -1, and this gives a rather simple pi term. We have L of L over D, so it's really the ratio of the length to the diameter that's important in this type of problem. Similarly, if we pick the roughness term with our repeating variables, go through the A, B, C, and nothing here for the length, we would find same result, that same type of result as the third pi term. We'd get that E over D is the dimensionless group, and that also makes sense because it's really the roughness relative to how wide the pipe is. So then we don't know the functional relationship. We'd have to do some experiments, but we could write that this pressure drop pi term is a function of the other 3 pi terms. And that's how we do these Buckingham Pi dimensional analysis problems.